next to the quantities that we have introduced before and that we have been using on both the artificial population and survey town, there are a number of very useful quantities that we will be using throughout, like, for example, the sample fraction. The sample fraction contains no new information, but looks at existing information in a different way, shedding new light on it and giving a new angle. So f is n divided by n. We need n and n. The sample size, lowercase n, the population size, uppercase n, and the ratio of that is the sample fraction. For example, in the Belgian Health Interview Survey, I have 10,000, roughly speaking, divided by 10 million, which is 1 per 1,000. It means if I would take the Belgian Health Interview Survey as a simple random sample, I would have a fraction of 1 per 1,000, 0.001, or 1 per 1,000. Of course, we know it's not exactly done in this way. There is stratification, multi-stage sampling, there is systematic sampling. So all of this amounts to the fact that the sample fraction may be different from stratum to stratum, etc. And the sampling probability is also for different people a little different. But it should somehow be not too far away from 1 per 1,000, so a few magnitudes. Okay, further, as we have said before, we have a population quantity, an estimand, the body mass index on average for the population, the sample quantity, which is the quantity that you compute in the sample, and the estimate, which is actually an approximation of the population quantity using only the n sample units. For example, the average is in the population the average of 10 million units, if we think of the Belgian Health Interview Survey. The sample average is the average of 10,000 units. So even though the two formulas look the same, except for some lowercase, uppercase shifts, there is a fundamental difference, of course. One is based on way more people than the other. But the thing is, yeah, there is the sample average, and there is the estimated average for the population, and for that I can use the sample average, but not for the total. The population total is the sum of all 10 million incomes. The sample total is the sum of 10,000 incomes. And what does it tell me? Well, the total income for the sample. If the population would be 10,000 people, yes, the sample is, but the population is not. So for that, and that's different between an average and a total, for that I need to scale it up by the inverse sample fraction. So the estimated total income about 10,000 people, so encompassing 10,000 people, I need to multiply by the factor 1,000 to get to the population as a whole. Which is why we have y bar, lowercase y bar, is the sample average, and that describes the sample, but also gives us an estimate for the population. For the sum, we use separate notation. Y, lowercase y as such, is the sample total. Y hat is the estimated population total through the sample. So it is the sample total, y, scaled up by the inverse sample fraction. Okay. Let's look at an example. Take the 6 samples of size 2 out of the artificial population, each having probability 1/6 therefore. Well, if I would estimate the sample average based on 1 and 2, I would get 1.5. Of course, 1 plus 2 divided by 2. For 3, 4, it's 3 plus 4 is 7. Divided by 2 is 3.5, and everything else in between. The sums are 1 plus 2 is 3. 3 plus 4 is 7, and the same for all other units. And then I have to say, well, what is the sample fraction? F is n divided by n, samples of size 2 out of a population of size 4, so that is 0.5. The inverse is 2, so to go from the penultimate to the last column, I multiply by 2, and I would go from 3 to 6, from 7 to 14, etc. If I do the same thing with replacement, I get the same result as before, except that now 1, 1, 2, 2, 3, 3, and 4, 4 are added. So with different probabilities, all right, but I now get also estimates from 1, 1, like on average 1, right? And 4, 4 on average 4. So you see what's happening. Among the 4 added samples in red, homogeneous samples, some of the estimates are more extreme than what they were before. And that's what I'm saying here. They happen to be the most extreme values. So we have several estimators. Here we have the estimated average, the estimated total, based on samples without replacement only, and then the same quantities, but there are more options because they're now based on all samples, also the ones that show replacement. Okay, so 4 estimators, when are they good? Well, 2 I cannot compare. The total and the average, they connect to 2 different estimates. Yeah, different but related, that's true. But I should not compare an estimator for a total with an estimator for an average, because they're looking at different things. But if I have 2 different estimators, or many different estimators, for the same population quantity, for the same estimate, then the question is which one is best. And that's essentially the question behind this entire course. If I'm interested in the body mass index for the Belgian population, on average, how should I draw my sample and analyze my sample so that I get the best possible estimate? And best means, well, statistically sound, valid, consistent, asymptotically normal if possible, but also precise, but at the same time, so that it can be obtained reasonably cheaply in terms of economic and fieldwork cost. All of that contributes. The statistical quantities that we use usually involve expectation, variance, bias, mean square error, etc. And then I can look at those and compare it to economical considerations. There are also formulas, and for some sampling mechanisms we will see them, but they're of course a bit more complicated because, yeah, what are the cost units, etc. There may also be some subjective judgment, etc. But before we go there, we have to redefine expectation and bias. And I know that many of you know what expectation and or bias is, but let's look at it in the notation and terminology of what we are studying here. A population out of which we take a sample. The expectation is the average of all possible estimates. And to indicate, let me go back. I can just as well take this one. These are all possible estimates of the average. So, what is the expectation? The average of the numbers in my ellipsoid. And the precision would be the variability in that column. That's all it is. So, I take all possible, not values from the population, no. Values across all possible samples. That's why I'm indexing by samples. Yeah, but in practice I only have one sample. Yes, I know that. And that's a consideration we will come to. In practice we only have one sample. But the concept is defined in terms of all possible samples. And it's still useful, as we will see. It is still useful, even though we may not take all possible samples. Well, you might do that, be my guest. But of course, you will be having quite a bit of work and quite a bit of cost, so that's not realistic. Okay, so for the total or for the average, of course, the expectation is entirely similar. When all samples are equally likely, for example, simple random sampling without replacement, the selection probability is 1 over S. So the PS is 1 over S if we sample simple random sampling without replacement. And then it's just the average, as I said earlier. If not, I need to take the proper quantity into account. And then bias. Bias occurs when you say the average, for example this, across all possible samples is not equal to the true population quantity, then it means that there is a tendency to be a bit too high or a bit too low, and we need to correct for that. So let's apply it to the artificial population. There, sampling without replacement, the expectation for the average is all the 6 values divided by 6, 2.5 as it should be. That's the population average. 1, 2, 3, 4, take the average, it's 2.5. For the sum, same numbers multiplied by 4, another surprise. I get a true population total. Of course, each and every sample individually is not guaranteed to yield the right value. I can get 6, I can get 14, or values in between. But the tendency is, just as a sake of thinking, just as a device in your mind, if you take a sample over and over and over and over again, sometimes it will be a bit too high, sometimes it will be a bit too low, but that nicely averages out. Of course, what does it help me to know that I'm way too high, but also I could have been way too low, so it's a good method? That doesn't seem to work. No, I agree with that. It's good to know that to begin with, but it's not sufficient. But we have a further device. We can increase the sample size to bring down way too high, to bring up way too low, so that the spread becomes smaller and smaller. If it can be a little bit too high or a little bit too low, and that averages out, then I have a precise, unbiased estimator, and that's what I want. Okay, if I sample with replacement, then of course we have to be careful. There are 6 values that can occur with probability 1 over 8, 2 over 16. Another 4 where it's 1 over 16, and the average, guess what, still is 2.5. And the same for the total, same reasoning. 6 values can come into being from samples that are heterogeneous with probability 2/16. The other are homogeneous with probability 1 over 16. And therefore, well, not therefore, but if you do the math, you will get also an unbiased estimator. So that's a summary. We have, for the average, for example, the population value 2.5. If we estimate it from samples of size 2, without replacement, we get an average across those samples 2.5. With replacement, still. So they're indistinguishable based on the information we have now. And if you would change the sample size, and do it, that's a good exercise. Change it to samples of size 1 and 3, for example, and if you really brave, or you have a lot of time, you can also do it for 4, but you will see that these numbers don't change. So we need the variance, we need the variability. What we now know is samples that produce a value that are too high compensate exactly samples that produce a value that's too low. But what we want to know is that the excess above and the deficit below in some samples nicely averages out. And that will be discussed in the next section when we deal with variability.